Welcome to lecture 4.5 on rational functions. Today's a little bit long lecture, so buckle up, folks. And it's a little bit confusing, so take your time, pause when you need to, and we got a break in the middle. So today for rational functions, we are going to look for a rational function. We're going to find the domain and graph of the function, identifying all of the asymptotes. We're going to solve applied problems involving rational functions. A rational function is a function that is a quotient of two polynomials, that is f of x equals p of x over q of x, where p of x and q of x are both polynomials, and q of x is not the zero polynomial, right? Which means that the denominator cannot equal 0. So here's an example of a rational function. F of x equals 2x plus 4 over x squared minus 4. Note that you can see that there's a polynomial in the numerator, 2x plus 4, and there's a polynomial in the denominator, x squared minus 4. And we know that with that, the domain of f consists of all inputs for x for which the denominator, q of x, does not equal 0. So for the example that we have given here, x squared minus 4 cannot be equal to 0. And if we do that, then we can see that x cannot be equal to plus or minus 2 if we solve that equation. So let's look at an example. Consider f of x equals 1 over x plus 4. Find the domain and graph f. Okay? Well, we know that the domain contains all the values except where the denominator equals 0. And when the denominator, x plus 4 equals 0, we have x equals negative 4. So the domain is everything but x equals negative 4, because the denominator really we should put cannot equal 0, and then you'd have x cannot equal negative 4. So the only input that results in a 0 in the denominator is negative 4. So the domain is, in set notation, it's x such that x cannot equal negative 4. Or in interval notation, we go from negative infinity to negative 4 with parentheses, union from negative 4 to infinity. This second one, a lot of folks mess up because they stop at negative 5 and on the other side put negative 3. But the parentheses tell us we're not including this value. So we go right up to the value negative 4 and start at that value negative 4 again on the other side, using parentheses to indicate that we do not include negative 4. And so we get this graph here. It's actually the graph of 1 over x translated to the left 4 units. Determine the domain of each of the functions shown below. Well, in this first one, our denominator cannot equal 0, so x cannot equal 0. So we have x such that x does not equal 0 in set notation, or negative infinity to 0, union 0 to infinity. Everything but 0. Here, x squared cannot equal 0. Well, that's the same thing, right? Because x squared cannot equal 0 gives us x cannot equal 0. When we solve that, the square root of 0 is 0. And so we have the same domain for both functions, although we do have different graphs. Now it gets a little more complicated for problem C anyway. Remember, when we have a polynomial like this, we have to find the zeros of the function, and one way we can do that is by factoring that function. Well, if we factor the denominator, we get x plus 2 and x minus 1, and we set that not equal to 0, which means that we set each of these factors not equal to 0, and so we get x cannot equal negative 2 and x cannot equal 1, and putting them in set notation or interval notation gives us these answers. Sorry about that. I'm always getting these weird clock sounds in the background, aren't I? I'm not even sure what that is. Okay, for the next one, it's a simple problem again. We set the denominator not equal to 0, and we solve, and we get x cannot equal to 3. In set notation, or negative infinity, comma 3, parenthesis, union, parenthesis 3, comma infinity. Again, in this problem C, we have another factoring problem. Here I didn't do the factors, but if you factor it, you'd find out that you'd have x plus 1 and x minus 2. And so you get the domain stated here in, again, set and interval notation. And then the last one is pretty straightforward. X plus 1 cannot equal 0, so x cannot equal -1. Rational functions often have vertical asymptotes. The vertical asymptotes of a rational function, f of x equals p of x over q of x, that's kind of our notation format, are found by determining the zeros of q of x, by determining the zeros of the denominator, and this is key, that are not also zeros of the numerator or of p of x. If p of x and q of x are polynomials with no common factors other than the constants, we need to determine only the zeros of the denominator. So if something is a zero of the numerator and the denominator, this means that it's a factor in both, okay? And that's the common thing, and we'll look at what kind of element that creates on a graph. If a is a zero of the denominator but not the numerator, then the line x equals a is a vertical asymptote. It is very important that you put this in this format, x equals a constant value, not just say that 3 is the vertical asymptote. No, x equals 3 is the vertical asymptote. It's always a line for the graph of the function. Determine the vertical asymptotes of the function. Well, the numerator is already in factored simplest form, but the denominator we can go ahead and factor. In the denominator, we get the factors of x plus 2 and x minus 2 when we factor the denominator x squared minus 4. We can see that neither of these are common or the same as the numerator, so we just have to find the zeros here. We set each factor equal to 0, and we get x equals -2 and x equals 2, which you can see in the graph. When we're graphing asymptotes, we graph them as straight lines using a dashed line on our graph, okay? Asymptotes are denoted on a graph by straight lines with a dash, and they are labeled with x equals when they're vertical asymptote. So here we have x equals -2, here we have x equals 2. It's that entire line where x equals 2. Let's look at another problem. Determine the vertical asymptotes of the function f of x equals x squared minus 4x over x cubed minus x. Now both of these terms can be factored, both the numerator and the denominator can be factored, so we want to go ahead and do that first, okay? Well, the numerator factors into x times x minus 4, and the denominator factors into x times x squared minus 1. Well, x squared minus 1 can also be factored even further into x plus 1 and x minus 1. Remember, vertical asymptotes are found only where the factors are not common. So we're not going to include this x factor because it's in both the numerator and the denominator. So to find the vertical asymptotes, we're just going to look for x plus 1, set that equal to 0, and x minus 1. And so we get vertical asymptotes are at x equals -1 and x equals +1. And you can see them with dashed lines on this graph. Now what happens here is that where the common element, the common factor in the numerator and denominator, which is x, where that equals 0, if it was factored into like x plus 2 or something, where that common factor is, we set that equal to 0. And when you have a common factor, what that creates on the graph is a hole, and that's what you see right here at 0, 4, okay? And we're going to do an example at the very end of this lecture that kind of walks through how to find holes in a rational graph. We also have something called a horizontal asymptote, or a horizontal line, okay? And in order to find these horizontal asymptotes, we compare the degrees of the numerator and the denominator. Now remember, the degree of a polynomial is the largest exponent. The largest exponent. So we're going to look for the largest exponent in the numerator and the largest exponent in the denominator. If they are the same degree, the line y equals a over b is the horizontal asymptote, where a and b are the leading coefficients of the numerator and denominator. These are the numbers in front of the variables with the largest exponent in the numerator and the largest exponent in the denominator. Okay? So for example, notice here we have f of x equals 6x to the fourth minus 3x squared plus 1 over 9x to the fourth plus 3x minus 2. Okay? We can see here that they are the same degree. They're both degree 4. And these are the leading terms, 6x to the fourth over 9x to the fourth. So the coefficients of these leading terms is where our horizontal asymptote is. So our horizontal asymptote is y equals 2/3. That's just 6/9 reduced. It's a fraction that's reduced to 2/3. All right? So when the degree of the numerator is the same as the degree of the denominator, we look for the leading terms and we take the coefficients of them, the fraction coefficients, and we have 6 over 9, or reduced, it's y equals 2/3. If the numerator is less than the denominator, the degree, again, we're talking about degrees here, then the x-axis, or y equals 0, is always the horizontal asymptote. Okay? So for an example here, we have 4 over x plus 2. Well, remember, a constant is a degree 0, because I could write the numerator as 4x to the power of 0, and the denominator here is a degree 1. So we have 0 is less than 1, the numerator is less than the denominator's degree, so the horizontal asymptote is y equals 0. Here's another example. We have 4x plus 3 over x cubed plus 2x plus 4. And again, we can see that the degree of the numerator, which is 1, is less than the degree of the denominator, which is 3. So this has the same asymptote, y equals 0. So whenever the degree of the numerator is less than the denominator, the horizontal asymptote is always at 0. If the numerator is greater than the denominator, then there is no horizontal asymptote. Okay? If the numerator is greater than the denominator, there is no horizontal asymptote. And here's an example there. 4x squared over x plus 2. The degree of the numerator is 2. The degree of the denominator is 1. So the numerator is greater, and there's no horizontal asymptote. Another example, 4x to the fifth over, plus 3 over x cubed plus 2x plus 4. Again, you can see the leading terms are in red to help you identify them, and the degree 5 is greater than degree 3, so again, there's no horizontal asymptote. So let's look at some pictures. The first thing is, let's graph 2x over x plus 3. Well, if we want to find the vertical asymptote, we set the denominator equal to 0, or I prefer not equal to 0 because that tells you at least what's not allowed, but x equals negative 3. If you do it this way, then it's giving you the equation of the vertical asymptote. So you can go ahead and draw that line from the top to the bottom. Then we want to find the horizontal asymptote. Notice the degree of the numerator and the denominator is the same, degree 1, degree 1. So our asymptote, our horizontal asymptote, is the coefficients in front of these two x terms. So we get 2 over 1, or simply y equals 2 is the horizontal asymptote. We draw the asymptotes with dashed lines, and then we compute and plot some ordered pairs, and then draw the graph. And here we have that graph. You can see the horizontal asymptote, y equals 2 in blue. You can see the vertical asymptote at x equals negative 3 in red. And then you can see some of these points that are plotted based upon our table here. Okay? You can slow this down. You can pause it and go back and listen again. But we're going to find the vertical asymptote through the denominator equals 0. And then we're going to find the horizontal asymptote by looking at the degrees of the numerator and the denominator. Let's look at another problem. Find all the asymptotes of h of x equals 2x squared plus 3x minus 5 divided by x plus 2. The first thing we're going to do is find the vertical asymptote by setting the denominator equal to 0, and we get x equals -2 as our vertical asymptote. Then we're going to look for our horizontal asymptote, and we can see that there is no horizontal asymptote because the degree of the numerator is 2 and the degree of the denominator is 1, so the numerator is greater than the denominator, which means we have no horizontal asymptote. Now, sometimes when the degree of the numerator is 1 degree greater, when the numerator is 1 degree greater, only 1, than the denominator, there is an oblique or slant asymptote. It's not vertical, up and down. It's not horizontal, side to side. It's at a diagonal or at a slant, okay? The way that we find this is to divide the denominator into the numerator, and the answer that we get on top, it will be our equation of a line that is our slant asymptote. So we divide the denominator x plus 2 into the numerator 2x squared plus 3x minus 5. I'm not going to go through this. We covered this in a prior section. And we get the answer 2x minus 1 with a remainder of -3. This 2x minus 1, if we graph the line y equals 2x minus 1, then this will actually be our slant or oblique asymptote. Okay? And you can see that there in blue. When the degree of the numerator is 1 greater than the denominator, you need to divide the denominator into the numerator to see and to find the slant or oblique asymptote. Now let's look at some basic rules here. An oblique asymptote occurs when the degree of the numerator is 1 greater than the degree of the denominator. We already talked about that. There can be only one horizontal asymptote or one oblique asymptote and never both, okay? You cannot have both a horizontal and an oblique because remember the way we find the oblique is that the numerator is greater than the denominator, which in and of itself tells us that there is no horizontal asymptote. And so if there is a horizontal asymptote, there cannot be an oblique one as well. An asymptote is really technically not part of the graph. It's really like a boundary line around the graph. You do draw it on the graph paper, but it's telling you a boundary line where the graph usually doesn't cross in most cases, and that's what we're going to talk about now. When can you cross an asymptote? The graph of a rational function never crosses the up and down, the vertical asymptote, but it's possible for it to cross over a horizontal asymptote. So you can never touch or cross a vertical asymptote, but you might at some point go across a horizontal. All right, that was a lot. So I don't know about you, but I sure could use a break. So why don't you take a break now, go get a little coffee, stretch out a little bit. We've been at this for almost 20 minutes. Maybe go get on TikTok and do your latest dance moves. You've probably seen me. I'm sure I'm trending like millions of viewers. They're like, who is that calculus math teacher with all those moves? And then you might also go for, oh no, we don't want a heartbreak. Let's get rid of that. All right, so we might pause here for a minute. Just get up, walk around. It's always a good idea after 10 or 15 minutes of watching a video to kind of pause a little bit. And then come back and we'll finish up the course. Not so much further to go. All right. So hopefully you've had a nice little break. You got a little coffee, you did some dance moves. I can show you some later. Maybe that's what I should do on our last video, is to do some dance moves. Okay, maybe not. That might be scarier than the math. Anyway, when we're graphing rational functions, the first thing we want to do is to find the real zeros of the denominator. Determine the domain of the function and sketch any vertical asymptotes. All this is saying is set the denominator equal to 0. When does the denominator equal 0? These are our vertical asymptotes unless, remember, there's a common factor in the numerator, and then that factor, when it equals 0, is actually a whole. Then we're going to find if there are any horizontal or oblique asymptotes, and we know how to do that now. We compare the degrees. If the degrees are the same, it's the coefficients. If the numerator is less than the denominator, the degree, then it's y equals 0, or the x-axis. And if the numerator is greater than the denominator, then there is no horizontal asymptote. And if it's only 1 degree greater, then it's a oblique asymptote, and we have to do the long division. Not very fun, I know. Then we find the zeros of the function. Determining the zeros of we do this by finding where the numerator equals 0. Whenever a numerator equals 0, the whole function goes to 0. And again, the zeros that we find are really the first coordinates of x-intercepts, right? We put that 0 value of x, say for example x equals 2 is a 0, well then the x-intercept would be parenthesis 2, comma 0. Then we want to find the y-intercept, okay? And we do that by plugging in the value of x equals 0 into the original function. And this gives us the y-intercept value of x equals 0, and then whatever we get from the functional value, whatever constants are there, we're going to get for the y value. And then we might use our calculator or plug in some values into a table to figure out other parts of the graph, other points on the graph, so we get the general shape of what's happening, and then we draw the graph. This is a good one to take a picture of maybe, or to make sure this is in your notes, how to go through and graph a rational function. So let's go through the steps here. Graph f of x equals x plus 3 over 2x squared minus 5x minus 3. So again, we're first going to find the zeros of the denominator by solving 2x squared minus 5x minus 3 equals 0. Well, if we factor this, we get 2x plus 1 times x minus 3. Setting each of those factors equal to 0, we get x equals negative 1/2 and x equals 3. And so the domain excludes those values. And we also know that these are where we have vertical asymptotes at x equals 3 and x equals negative 1/2. And remember that we will graph these or sketch these on our graph using a dashed line and labeling them x equals 3 or x equals as part of that value. Because the degree of the numerator is less than the denominator, the x-axis, y equals 0, is the horizontal asymptote. So we don't have to calculate anything here. We just can see that immediately, since the degree of the numerator, which is 1, and is greater than the degree of the denominator, which is 2, then the horizontal asymptote will always be the x-axis, or where y equals 0. Next, we need to find the zeros of the numerator. We only have x plus 3 in the numerator, so we solve that by setting x plus 3 equals 0. Thus, negative 3 is the 0 of our function. And the pair negative 3, 0 is the x-intercept. Lastly, we find the y-intercept by plugging in 0 into the equation. We get 0 plus 3 over 2 times 0 squared minus 5 times 0 minus 3. Notice what this does is it just leaves us the constants that are in the function, because everything else with an x goes away. So we get plus 3 over minus 3 just by looking at the equation. This is one of the easiest parts to do, because only the constants are left. And so we get the y-intercept is at negative 1, so this would be 0, negative 1 as far as a point on our graph. We find other function values by calculating a table, picking some random values between the intercepts, particularly the vertical intercepts, or the asymptotes, I mean, and then we plot the points. Remember that we plot asymptotes with a dashed line. Here we can see the 2 vertical asymptotes in red, and you can't see really so well when it's on the x-axis, but you can see that the graph is getting closer and closer to the x-axis, but not ever quite touching it. So let's look at a few more examples for this course. I'm going to go through these pretty quickly, just so you get a feel for it. You can pause at any time and look at these. All right. So when we look at the first one, we get the vertical asymptote, which is setting the denominator equal to 0 as x equals negative 2. For the horizontal asymptote, we can see they're the same degree, so it's the coefficients in front of the leading terms. There's a 1 over a 1, which is equal to 1. So y equals 1 is our horizontal asymptote, you see in blue. You see x equals negative 2 in dashed red. Our x-intercept is where the numerator equals 0, right? And so we get 3, 0. our y-intercept, we plug in 0 and look at the constants that are left, so we get -3/2. And we can see those points here. There's our y-intercept at -3/2. There's our x-intercept at 3. We would also plot some more points and see the general shape. For b, we have f of x equals 8 minus x squared over x squared minus 9. Again, if we factor the denominator, we get x plus 3 and x minus 3. So we can see our vertical asymptotes are at x equals -3 and 3. Again, we have the numerator and denominator have the same degree, x squared, so we look for the coefficients. In the numerator, I have a -1 in front of the leading term, and in the denominator, I have a +1. So -1 divided by +1 is simply -1, and so we have y equals -1. We can see that horizontal asymptote blue here at y equals -1, it's all the way across. We can see the vertical asymptotes in red at x equals -3, and at x equals 3. The x-intercept, again, we find by setting the numerator equal to 0, so we get 8 equals x squared. And so what happens here is we actually have 2 points, because when we're doing the square root of 8, we have to take the positive and negative value of that, and we get 2.828, positive and negative. And then to find the y-intercept, we simply plug in zeros for x, and we get 8 over -9. The constants are the only thing left, and so we get -8/9, which we can see here. For c, we have x squared over x plus 1. Again, the denominator we set equal to 0 to find our vertical asymptote, and we get x equals -1. You can see it as this red dashed line. Here we have the numerator is greater than the denominator, so there's no horizontal asymptote when we're talking about degrees. The numerator degree is 2. The denominator degree is 1. But it's 1 degree more, so we have to figure out if there is an oblique asymptote by dividing the denominator into the numerator. Now remember, in this specific problem, when you do that, this would be x plus 1 into x squared plus 0x plus 0. You'd have to put those zeros in there so that you can do the long division. When we plug, when we're looking for the x-intercept, we're going to set the numerator equal to 0 until we get 0. And for the y-intercept, we set all the x's equal to 0 until we get 0 over 1, which also gives us 0. So the x and y-intercept are actually the same in this problem because they occur at the origin. So let's look at one final example where there's a hole in the graph, okay? So we have g of x equals x minus 2 over x squared minus x minus 2, okay? If we factor the denominator, we get x plus 1 and x minus 2. And so immediately we can see that there's a common factor here. So this means we will not have a asymptote, a vertical asymptote at x equals 2. Instead, at that value, we're going to have what's called a hole. Okay? When you have a common factor in the numerator and the denominator, where that equals 0, you have a hole. Okay? The domain of the function is that x cannot equal -1 and x cannot equal 2. It's still the same, even though we think about canceling these out. And we will do that when we're graphing. But right now we have to remember this original function cannot equal 2 in the denominator because it makes it go away, even if we reduce that, because that changes the function. The numerator and denominator have a common factor, x minus 2. The zeros of the denominator are -1 and 2, and the 0 of the numerator is 2. Since -1 is the only 0 of the denominator that is not a 0 of the numerator, the graph of the function has x equals -1 as its only vertical asymptote. If we simplify the expression, we get, by canceling out the x minus 2 factor, we get simply 1 over x plus 1. And this is what we will graph. When we plug in 0 for x, we get y equals 1, and that's the y-intercept. There is no x-intercept because there's no x variables left in the numerator, so to speak. So the graph of the function y equals 1 plus x plus 1, 1 over x plus 1, is the graph where the point where x equals 2 is missing. So we have to find the y value here. So we get, when we plug in 2, where the hole is, we get 1 over 2 plus 1, or 1/3. So the hole is going to be located at 2, comma 1/3. And if you look at this graph, you can see that. We have our graph here, we have our graph here. We do cross the x-axis at, no, that's the y-axis. We don't ever actually cross the x-axis. And we can see there's a hole at 2, 1/3. Okay? That's been a long lecture. Thank you guys for hanging in there. Hope you had a good break and a good TikTok dance. And that's the end of today's lecture. See you next time.